Another minimum spanning tree algorithm is Kruskal's algorithm. Kruskal, much like Prim's, takes a graph and returns a minimum spanning tree defined by a set of edges. The approach that's taken by this algorithm is very different and is actually very elegant. Let's take a walk. Let's look at the pseudocode first, and then we'll walk through an example. So you see the input and the output to the algorithm, and there is an initialization that takes place in a for loop. And what that does is it creates a unique set, one for each vertex in the graph. So each vertex occupies a set by itself, okay? So if there are cardinality of V vertices, there are cardinality of V sets, each having a single distinct vertex. The edges to the individual graphs, the edges in the graph are then sorted and placed into a min queue, and so the edges are pulled off in increasing order, meaning it's a minimum queue. And if the edge that is removed comes from two different sets, that edge is added to the minimum spanning tree, and those two vertices are unioned into the same set. And I think it's best to actually go through the example and see what we mean. But once again, I want to make sure that we're taking this forward when we go into the example. So we start with a set number of sets, each having a single vertex, and we place all the edges by weight into a priority queue, a min queue, and we remove the edges one at a time. And if the endpoints for the edges are in different sets, we will keep that edge in our minimum spanning tree, and we will union those vertices into the same set. Otherwise, you notice that we do nothing. Okay, otherwise, in that instance of in that iteration of the for loop, we do nothing because the if fails, and so we fall through, and then we go back and execute the next iteration. Let's take a look then at an example. We will use the same graph that we used for Prim's algorithm, and so it's this graph, but we will see that this is a very different algorithm. So let's set up our priority queue, and so we place all these edges into a priority queue, and we get one that is like the one on the right. Obviously, our priority queue could differ. The order of these could differ when the edge weight is the same. So really having BD above CD would be absolutely fine. Same thing with these three edges. They could be in any order, and these two edges can be in any order. And so these are the edge weights. So BC has weight 1, that's this edge, followed by CD, which has weight 2, and that's this edge. But BD also has weight 2, that's this edge, and that's the next one, and so on. Okay, and here are our distinct sets, and we're going to color them differently so that we keep track of which set is which. So at this point, we have 6 distinct sets. Each one of these sets has a single vertex. There are no edges in the minimum spanning tree at this point. And so let's pull off our first edge. That's edge BC. And if we will recall the algorithm, The algorithm says that if B and C are in different sets, we keep the edge and we union the sets. And so that looks like this, okay? And because B and C are in different sets, you notice we put a checkbox here saying we will keep that edge, and we now union those into the same set. So we now only have 5 sets. There's 1 set of 2 and 4 sets of 1. Okay, we will now pull off the next edge, which is edge CD. Edge CD is the edge that goes right here. Well, it's connecting C and D, which are in different sets. So we're going to accept that edge, okay? And we're going to union D into the set that C is in, which also includes B. Okay, so we now are down to 4 sets, 1 set of 3, and 3 sets of individual vertices. Okay, now the next edge that comes off is the edge BD. You notice that B and D are in the same set, so we will reject that edge. Okay, so we reject that edge and we fall through that iteration and we pick off the next edge. CF is this edge here. It's going to vertices that are in different sets, so we will accept that edge. That means we will put it in our minimum spanning tree, and we union the sets to now include F. And we now have 3 sets, one that has 4 vertices and 2 that have that each have a single vertex. The DF edge is next. You notice that DF are in the same set, so we will reject that edge. Okay, the EF edge is the next edge to be considered, and E and F are in different sets. And so we accept that edge and we union E into the set, the set of the minimum spanning tree set. And you notice now that we're down to 2 sets. The next edge that comes off is the AD edge. The AD edge emanates from different sets, so we will accept that edge and we will union A into the minimum spanning set. Now that everything is in the minimum spanning tree, we simply reject. We stop processing. That's the equivalent of rejecting all remaining edges. And the minimum spanning tree cost is 14. It's the same graph as that was used in the Prim's algorithm demonstration. Where do we get the 14 from? Well, let's look at these edges. The AD edge is 4. And the BC edge is 1, and the DC edge is 2, CF is 3, and EF is 4, and 4 plus 3 is 7, plus 2 is 9, plus 4 is 13, plus 1 is 14. You notice that if you go back and look at the Prim's at the Prim's algorithm video, you'll see that we got a different set in this case. I believe the Prim's had there was something different. I know that this edge was taken in the Prim's demonstration. So go back and look at that. But the cost for both of those is the minimum spanning tree cost. It is 14 in both cases. The only thing that may change is the edges, is the set of edges that we pull off. And that is an example of a minimum spanning tree using Kruskal's algorithm.